In this video, we're going to go over program-derived addresses. This is a Solana feature that allows us to deterministically derive account addresses using some predefined inputs. The optional inputs we call seeds, then a bump seed is an extra byte we add as an input, and then the final input is a program ID. There are two things to note about PDAs. One is that PDAs do not have corresponding private keys, so they cannot cryptographically sign messages. The second thing to note is that programs can sign from PDAs derived from their program ID when making cross-program invocations. This is a Solana feature where one program directly invokes the instructions of another program. We'll cover that in a different video. For this video, we'll just focus on how PDAs are derived. So here's a visualization of how PDA derivation works. When we call find program address, we pass in the optional seeds and a program ID. Under the hood, this will add a bump seed starting with a value of 255. Our optional seeds and bump seed and program ID are then passed to create program address. If a valid PDA is found, meaning the address that's generated falls off the 825519 curve and does not have a valid private key, then the PDA and bump seed are returned. If not, we decrease the bump seed by 1, so going from 255 to 254, then call find program address again with a new bump seed, and we go through this loop until we found a valid bump seed, returning the PDA and whatever the bump is that generated the valid PDA. Next, let's walk through this first example. So on Solana, we generally use the public key of an 825519 key pair as the address of an account, and a public key has 32 bytes and has a corresponding private key, also known as the secret. Now, a key pair is a point that falls on the 825519 curve, so it has a public key and a private key. A program-derived address is an address with 32 bytes that looks like a public key, but falls off of the 825519 curve, so it does not have a corresponding private key. A PDA is derived using some optional inputs that we call seeds, and a program ID, and a bump seed, which is an extra byte that we use to guarantee that the output of the PDA is an address that falls off the curve. One thing to note is that when you generate a new key pair or derive a PDA, it does not automatically create an on-chain account at that address. So at this point, there is no data associated on the network at these addresses. We're simply generating addresses that can be used as the address of an account. However, we would still need to invoke the system program to create an on-chain account at any particular address. You can think of generating addresses as picking random coordinates on a map. Just because you have the coordinates doesn't mean there's anything at that location. So if we were to run the example, we would get the following output. Here we have the public key and secret key for the key pair that we generated, and the is_on_curve check returns true. For the PDA, we have the following address that we're calling the program ID and the output PDA along with its bump seed, which we've derived here. The is_on_curve check returns false for the PDA because the PDA has no corresponding private key. Next, let's go over two more examples. In the first example, we're deriving a PDA where the optional seed is a hard-coded value of admin. In the second example, we're deriving a PDA where we use multiple seeds. The first seed is a hard-coded value, the second seed is a public key, and the third seed is a number. When we run the example, we get the following output. In the first example, we get the PDA and a bump seed with a value of 255. In the second example, we get the following PDA with a bump seed of 253. Note that if we run the example again, we get the same addresses and the same bump seeds. Next, let's go over how PDAs are derived. When we call this find program address function, we pass in the optional seeds and a program ID, and it gives us back a valid PDA and a bump seed. The bump seed is an extra byte that's used as an input to guarantee that the program-derived address returned by this function is a valid PDA that falls off the 825519 curve and therefore does not have a corresponding private key. Under the hood, find program address calls create program address, so we can get the same PDA using our optional seeds and including the bump seeds and passing the combined seeds to create program address. If we were to run the example, we get the following output. So here we can see that both addresses output from find program address and from create program address generate the same address using the same bump. And just as before, if we run the example again, we get the same addresses because the PDA was derived using the same optional seed, same program ID, and same bump seed. Next, let's go through an example to visualize how this works. We're going to use the hard-coded seed, hello world, and some random address that we're calling program ID. When we call find program address, we pass in the seed and program ID just as before and get back the PDA and bump seed. And we're going to go ahead and print the bump and seed. We're also going to loop through all possible bumps starting from 255 all the way down to 0, passing in the same seed and bump seed for every value of the bump, and calling create program address, printing the bump and PDA if a valid one is found, and printing invalid PDA if the combination of seed and bump seed generate an invalid PDA. So when we run this example, we get the following output. We have the program ID and the seed, and the output from find program address. Note that the bump seed is 252, and this is the PDA that was found. When we iterate through all the bumps and call create program address, note that the bump values 255, 254, and 253 all have generated invalid PDAs, and it's at 252 that we get our first valid PDA, which is what's returned by find program address. Now, the first bump seed that generates a valid PDA is commonly referred to as the canonical bump. Note that there are different values of the bump that also generate valid PDAs, except with different addresses. As a security best practice, you generally only want to work with the canonical bump when using PDAs.